Hey, all you cool cats and kittens. It's Mr. Smith back with you for a new unit. Today we're talking about waves. Hopefully, you are as excited as I am about them. So, if you take a look at the screen, you'll see this beautifully crafted PowerPoint has got several different waves. They all involve water. Turns out, water is way too complicated for what we're going to talk about. We're going to talk about sound waves and light waves. So, get excited for that. So yeah, we got two types of mechanical waves. So mechanical just means they move based on like physical properties, science stuff. We got the transverse wave. That's a wave vibrating perpendicular to the direction it's traveling. And an example would be light waves. So what I've got for you is, oh, it's a GIF. Do you see it? So it kind of looks like almost like a flag, you know? That was kind of what I thought the first time I saw it. All these particles are supposed to represent, let's just say, water particles or air particles. Could be any sort of like atom, but like really, really small. And you'll notice that the particles, if we just focus on one here, you'll notice that it's only moving up and down. It's not moving anywhere side to side. That's what a transverse wave is all about. Only moves up and down, even though the wave is moving from left to right. So the particles move up and down perpendicular to the direction the wave is traveling. Kind of cool. The next thing we have is called a longitudinal wave. Now, instead of going up and down, the particles are going to travel with the wave. What that ends up looking like is it ends up looking like this GIF right here. So what you'll notice is that particles will get caught by a wave and then they'll kind of travel forward a little bit and then they'll be released by the wave and kind of fall back in their spot. So what this looks like is you'll see this a lot of times with sound actually, where these air particles that are kind of all close together are compressions of sound waves, and then behind those compressions of air you have little empty spaces. So right here is a compression, behind it is some empty space, and that kind of creates its own sort of wave. But instead of moving up and down, now the wave, the up and down part is kind of happening with the wave. I don't know. Longitudinal waves are kind of tough. So we're going to focus for most of this unit just on transverse waves. But it is kind of, I thought this was super cool when I saw it. So I figured I had to show it to you guys. Let me see what I'm saying. Anyways, moving on here. Here's an ocean wave. Here's a wave in a pond. Now, one of the things you might notice is that these ocean waves and these waves in the pond, they don't look like the waves we've shown you. And that's because it turns out water actually has both things going on. It's got transverse and it's got longitudinal. So actually what happens is you'll see in this GIF there's one or two particles that are being focused on. A particle closer to the surface is actually kind of just moving in a circle as the wave moves. I saw this, I thought it was super dope, so I figured I had to show it to you guys. Waves in a pond, very similar type thing. Here, instead of it looking a little peaky, now it looks more rounded at the top. And you'll see that the path the particle travels is a little bit less circular and a little bit more of an oval. Something you'll see in both these pictures is that water particles are moving different amounts. It looks like the particles on the top move the most and the particles further down move the least. You'll also notice if you kind of just look like straight up and down that some particles are moving up a lot, some particles are moving side to side a lot, but they're all kind of doing both. You won't really find a particle that's really standing still, or if it is, it's like barely standing still. So if you just kind of focus on one particle at a time, you'll notice sometimes it's moving up, sometimes it's moving left or right. So that's just to say that they have both transverse and longitudinal patterns. Here's what a transverse wave would look like if we put it on a graph down below here. It just, sometimes it's up, sometimes it's down. This picture down here at the bottom is what we're going to focus on when we're talking about waves. So know that this is like a very simplified version of what waves are, but we're going to keep it kind of simple. If you want to get more complex like this is collegiate level wave replication. I guess. So I don't really understand it because I didn't go to school for waves. I went to school for chemistry. Anyways, here, transverse waves. Here's a wave. That's the same picture from the last slide. Most waves behave like this to some extent. They don't exactly look like this transverse wave because there's more complex things happening. If you want to study more complex waves, you're going to have to learn more complex physics. But they do behave similarly. So when we're talking about waves, we'll talk about light a lot and sound a lot because those are kind of smaller events than like an ocean wave. So it's a little bit easier to kind of simulate what they look like. Two definitions you're going to want to know is crest and trough. A crest is the top of a wave, and a trough is the bottom of a wave. So go ahead and write that down. Crest is the top, trough is the bottom. Two parts of a wave. We're also going to talk about a couple other parts of waves. So moving on here to the next slide, you'll see here's another wave. This here looks just a little bit different, but you'll still notice that it's got peaks and valleys, which we're calling troughs and crests. First thing I wanted to show you is I wanted to show you in blue here, lowercase a. Lowercase a stands for amplitude. Amplitude is measured in meters. This is the height of a crest or a trough of a wave. So kind of at its highest point and at its lowest point, what's the height of this wave? Amplitude, more commonly heard of as amps in the realm of sound, has to do with how loud something is. So if you crank up the amplitude, your sound is going to increase. Fun fact. Over here next, we see this, it kind of looks like an upside down Y in green here. That is called lambda, is the name, L-A-M-D-A, I think is how you spell it. And that stands for wavelength. So lambda equals wavelength, also measured in meters. And that's the distance between two equally high points on a wave. So up top here, I've got the two crests. From crest to crest, that right there is a wavelength. Here at the bottom, from trough to trough, that's another wavelength. You'll notice if you kind of compare these two with each other, they're the exact same distance. So a wavelength is always going to be constant for a sound or a thing of light, for example. So red light all has the same wavelength. Or a certain like sound would have a certain frequency, would have a certain wavelength. So like a radio, 101.3 would have the same wavelength type deal. Or I guess a pitch of a note would also have the same wavelength. Once again, we don't have to necessarily measure it at crest to crest or trough to trough. We can measure it somewhere in the middle as long as we're at that same height. So you'll notice here there's two more different measurements of wavelength I have shown here. All four of these are all the same length. I actually just copied pasted it so I know that they're exactly all the same because I'm also in chemistry or physical science. Now, this whole act of kind of starting at a crest and then going up to a crest, that is called a cycle. So a cycle is another term you're going to want to know in addition to amplitude, wavelength, cycle. Have those three written down. So the action of going from crest to crest, trough to trough, or any equally high point to any equally high point, those are cycles. So on the next slide here, I've got more information about cycles, more visuals about cycles. What you'll see here is you'll see three different graphs. It's the same wave, it's just kind of shown a little bit differently. In this first one, in this first wave, it's a different type of cycle. So you'll notice there's a blue part, and then like a dark brown part, and then maybe a yellow part and a black part. Here, each cycle is going to start and end at 0. So it's going to start at 0, have a crest, have a trough, and then arrive back at 0. Once it's reached that 0 mark for the second time, crest, trough, and then 0, it's going to start a new cycle in brown and then a new cycle in yellow. Oops. Over here, our second cycle, or our second graph, the cycle starts at the crest and ends at just before the start of the next crest. And then in blue, crest to crest, green, crest to crest, orange, crest to crest. If we were to measure any of these at the 0 point, the crest, or the trough, we would notice that they all have the same wavelength. So if I measure it from this first one, from blue trough to orange trough, that's the same as measuring it from 0 point to 0 point. So a cycle is kind of the same. It just kind of depends on what the wave looks like. Where do you read it? Do you read it at crest to crest, trough to trough, like this third graph, or 0 point to 0 point? If you get further into math, which most of you will do, you'll start to realize that this first graph here is a sine wave, and this second graph is a cosine wave. That's kind of fun. I don't know. I thought it was. And this third one is, I don't know, it's like a cosine or a sine, but shifted a certain measurement. I don't know. A math teacher could probably tell you more about what exactly that wave is. So feel free to ask them. Feel free to send an email and be like, hey, what kind of graph is this? Here's another wave. This is just one cycle right here. This is a sine wave. You don't need to know that. What I want you guys to do right now is take a look at these two questions. What's the amplitude of this wave? And what's the wavelength of this wave? Sound good? Go ahead. Hopefully you get the answer for amplitude. The amplitude of this wave is going to be 5. Because at its highest point, it crests right at that 5 mark, and at its lowest point, it troughs right around at that 5 mark. So you'd rate it as 5 or 5. Common misconception here would be to say the amplitude is 10 because it goes from 5 to -5. Amplitude is not 10. We're just looking at from the 0 point, what's the highest point? Or from the 0 point, what's the lowest point? And those will always be the same for waves. The wavelength of the wave here is 1. Lambda equals 1 meter because that's where it starts at the 0 point and then ends at the other 0 point. Common mistake here would be to say half if you're only counting the crest and not counting the trough. So remember, you have to measure from the start and end at the same place. So one cycle would be going up and down and then back to the original starting point. Or going up, then going down, then going back up. Or starting down, going up, and then ending down. Either way, that would be measuring a full cycle. And that's what wavelength is. It's measuring a full cycle in meters. Another term that we're going to talk about now, you'll notice what's different about this graph from the last one, is that now we're looking at it not in terms of distance in meters, but in time. And the new term we have for you guys is period. So period is kind of like the wavelength equivalent, except now we're in time. So if we're talking about a wavelength, that's a distance, but time is kind of looking at a wave, how much time does it take for one cycle to happen. So that's big capital T. It stands for period, and it's measured in seconds. The other thing we are going to talk about is frequency. So frequency is lowercase f, and it's abbreviated with, it's got the unit hertz, capital H, lowercase z, and that is the number of waves per second. So here you'll notice that it completes 1 cycle, 2 cycles, 3 cycles, a total of 4 cycles in 1 second. So the frequency would be 4 hertz. F equals 4 hertz, or 4 cycles per second. Fun fact, hertz stands for, it's a calculated variable. It's the same thing as 1 divided by seconds. So in this case, 4 hertz means 4 cycles per second. Sound cool? Great. Here are some questions on the next slide. First question is looking at wave number 1, wave number 2, assuming they have the same height and the graphs stretch over the same distance, which wave would have a higher frequency and which wave would have a longer wavelength. Hopefully you got an answer. Let's go over them. For which one has the higher frequency, we're looking at the one that completes more cycles per unit time. So since these guys here are more scrunched together, we would say that graph number 1 has the more cycles per time, so graph number 1 has the higher frequency. Longer wavelength, if you have a high frequency, you're going to have a super short wavelength. Look at how quick that wavelength is compared to this other wavelength on the second graph. So since there's a higher distance from crest to crest, or trough to trough, or 0 point, 1 0 point to the next 0 point, we would say that graph number 2 has a longer wavelength. Hopefully that makes sense. hopefully you guys are feeling better about terms like amplitude, frequency, wavelength, cycle, crest and trough. Those are all kind of fair examples to be on your homework coming on up here. So thanks for watching. I miss you guys so much, and have a great rest of your day. Take care.